Welcome to this lecture. This is lecture number 4 from week 4. We have been discussing about finite sums of random variables and more generally certain weighted sums. In the previous lecture, we have discussed about techniques from real analysis which helps us looking at the convergence for such weighted sums of random variables. Now, in this lecture, we are going to continue looking at the similar type of properties, but now with probabilistic methods. We are going to see that independence plays a very important role in these type of analysis. Without further delay, let us continue discussion using the slides. So, we are following the standard terminology and notations that we have a fixed probability space on which we are given a sequence of random variables, and we are now interested in the problem of the almost sure convergence for the corresponding series of random variables. Now, as we have discussed in the previous lecture, corresponding to this series we are essentially be interested with this sequence of partial sums defined this way. So, for each n we are looking at the sum of first n many random variables coming from the sequence, and as long as this sequence of partial sums converge, we talk about the convergence of the corresponding series. So, in the previous lecture the discussion that we had was using results from real analysis and how this can be useful in estimating or talking about the properties of finite such sums of random variables. And then using such results we can also talk about the corresponding convergence of the random series. But now what we are going to focus on are probabilistic methods, and here we are going to assume that the random variables in the sequence are independent, and we are going to see how this can be useful in obtaining estimates of this sequence of partial sums. First, we should be clear that almost sure convergence for the series that we are interested in means that we are talking about convergence for every sample point to a finite limit, meaning if we fix a sample point and evaluate the corresponding series, that should converge to a real number, and that should happen outside a set of measure 0. So, that is the type of almost sure convergence we are interested in. Now, some few comments before we look at this specific type of a problem. First, note that x is in L1, that means that x is integrable in the sense that expected value of mod of x is a finite quantity, and moreover expected value of x should be taking values in the real line. Now, if you assume more conditions like the L2 integrability, which means that we are asking about the finiteness of the second moment, then we have of course the finiteness of the first moment by this standard inequalities that we have discussed earlier, and moreover if the second moment is given to be finite, then we also can show that all the second moments about any point C is also finite, and by looking at the infimum of those we end up with the variance of the random variable, and in this case under these assumptions this also turns out to be finite. So, now let us say that we take two random variables again from the L2 space, then as we have seen earlier that Cauchy-Schwarz inequality helps us showing that the expected value of mod of x y is also finite, that is the first absolute moment of x times y that is finite. Now, in particular we also have that expected value of x y is in the real line. Now, from this finiteness what you are essentially having is that x times y is coming from the L1 space. Now, in this case what we have is that the expected value of x times y, that is a real number. Now, if you assume that x and y are independent, then you can perform this set of standard calculations that expected value of x times y, that is by definition integral of this quantity with respect to the probability measure. Now, if you change variables, then we end up with the probability law of the random vector x y. So, that is what we are using for the transformation rule, and then the integration changes to over the R 2 and we have to now integrate x times y, where x y are coming from R 2. Now, here if you do this integration, we note that by the assumption of independence, we end up with the factored probability measures like this. Remember, this is the discussion we had in week 2, that if x and y are independent, then the joint law of the random vector factors out into the product of marginals. So, that is what we are writing here. Now, we appeal to the fact that here we have separated variables in the integrand, and moreover we also have the existence of the separated integrals, and here we appeal to Fubini's theorem to say that this two dimensional integration can be written as this product of integrations. So, this is essentially writing the two dimensional integral as iterated integrals, but then again since the variables are separated in the integrand, we end up with product of two one dimensional integrals. But these each of these finite one dimensional integrals are also existing, because we have assumed the integrability conditions coming from L 2, and therefore, these expectations on their own also exist. And therefore, what we have ended up showing is that expected value of x times y is the product of the expectations. So, this is true whenever we have two random variables coming from L 2 and we are assuming them to be independent. In particular, this observation that the expectation of x times y as long as they are independent factors out, this leads to an interesting property in terms of covariances and correlation of the random variables. So, these are all standard facts that you have seen in your basic probability theory, but there we had to deal with the situation when both the random variables x and y were discrete or both of them were absolutely continuous. Here we are making no such assumptions, x and y as long as they are in L 2, so that all the corresponding expectations exist, we can perform these calculations. And this is the essentially the application of measure theory that allows us to take, for example, one of them to be discrete and the other to be absolutely continuous, or even from the mixture distributions. All right. So, let us continue. So, now in this situation, if we take the covariance of two such random variables, which we denote by the standard notation cob of x y, then we can look at the definition, which is this one. Now, this can be simplified, as we are all aware of that we perform these calculations that you may have seen in your basic probability theory, that this simplifies to this expression. But now, as long as the two random variables are independent, this expected value of x times y is the product of the expectations, and hence the covariance becomes 0. Now, again I repeat, x and y need not be discrete or absolutely continuous, they can be any kind of mixture distributions also. Now, here what is happening is that as long as the covariance of the two random variables is 0, we end up having the fact that x and y are uncorrelated. So, therefore, what we have proved is that two random variables, if they are independent, then they are also uncorrelated. Now, moreover, you can also perform this calculation for the variance. Remember again, as long as x and y are coming from L 2 space, then x plus y is also in L 2 space. So, therefore, we have finiteness of the second moments, and here we can look at the infimum over all such second moments about the point C, and that is essentially the variance of x plus y. Now, if you simplify this, the infimum is achieved at this point when the constant is taken to be the sum of two expectations, and if you simplify this, then we end up with this expression. So, this is a standard algebraic simplification that you can do. But now, if x and y are uncorrelated, then the covariance is 0, and therefore, the variance of x plus y is variance of x plus variance of y. So, in general, if x and y are independent or if they are uncorrelated, then you can have this relation involving the variances. But now, if we go back to our original assumption that we have certain number of random variables which are independent, then we can look at the variance of this partial sum, the Sn. Now, these Sn's are again x1 up to xn, the addition of these random variables, and then if they are independent, then by this previous observation the variance of Sn simply turns out to be the summation of the individual variances of the random variables. We are going to use this observation in our later calculations in this lecture. But now, here we go back to this very classical old problem that you should find examples that uncorrelated random variables need not be independent. So, in general independent random variables are uncorrelated, meaning the covariance between the random variables are 0, but the converse need not be true, that if you have uncorrelated random variables, you can find examples where the two random variables are not independent. So, take this as an exercise. So, this you have seen in your basic probability courses, but please try to recall these facts. Another important exercise is that so far we have assumed that x and y are coming from the L2 space, but these same calculations, at least a part of them can be performed if you assume them to be only coming from L1. The assumption is now that the random variables are independent and they are L1 integrable. Then you can show that x times y must be coming from L1, in the sense that x times y has finite first absolute moment, and moreover in this case as long as you have the finiteness of the expectation of x times y, you can show that again it is becoming the product of expectations. Please take this as an exercise. So, this is just an extension from the calculations that we are performing in the L1 stage, but you may have to do some more work to show that the same results continue to go through, and in particular we should first establish that x y is L1 integrable. All right. But now, we go into the main results of today's discussion. We start with this important theorem, which is talking about a certain inequality due to Kolmogorov. The result says that as long as we have assumed that all these random variables x1, x2, xn and so on are independent, and if they are coming from L2, then you have for every epsilon positive the maximum of Sj minus expected Sj, the modulus value of that exceeding epsilon is less than variance of Sn over epsilon squared. So, here what are the main assumptions, that x1 up to xn and so on, these are all independent. So, that is the first assumption, and to ensure the finiteness of all the moments that we want, they are all coming from L2 space. So, this is the assumption that we are using in this setup. Now, here what we are having is that the maximum of these quantities exceeding any arbitrary epsilon can be dominated from above in terms of the variance of Sns. Now, let us go back to the standard inequality, which is the Chebyshev's inequality, and try to understand the importance of the Kolmogorov's inequality. You see, if you fix one single random variable, then we immediately have this bound that modulus of x minus expected x exceeding epsilon, the probability of that can be dominated from above by variance of x over epsilon squared. But now, what we are saying is that in the presence of independence of all these n many random variables, you can actually get something involving the maximum of these quantities exceeding epsilon, that also can be dominated by a single quantity. Now, you do not have to look at each individual Sj's, you have to just look at the final partial sum, which is Sn, and then taken together the maximum of these quantities exceeding epsilon, that can be dominated in terms of the variance of Sn. So, that is the usefulness of Kolmogorov's inequality. So, let us try to write down a proof. So, first of all we observe that we can assume that all the random variables are having mean 0. So, this can be assumed without loss of any generality, and if we assume that all the random variables are mean 0, then in particular all these partial sum random variables which are Sn, they also have mean 0. Now, let us focus on the main event that we are interested in. So, now remember we are looking at, in general statement we are looking at maximum of j between 1 and n, where we are looking at the terms Sj minus expected value of Sj exceeding epsilon. So, this is the quantity that we are interested in. Now, as long as these expectations are 0, this description just reduces to this. Now, that is the event A that we denote. Now, whenever the maximum of these n many modulus of Sj's are exceeding epsilon, then we can ask what is the first j for which this lower bound is true. Meaning, suppose you might have first j minus 1 many cases being less than epsilon, but it is the first time that for some j this bound is achieved. Meaning, the maximum is first observed as long as you look at the first j here. So, that is the event A j that we are looking at. Now, among these n many random variables, if S j is the first time you exceed this epsilon, that is the event that you are looking for, and therefore, you need to look at for all values of j 1 to n, what is the first time this is exceeding. So, you will have n many such events Aj's. But now, since you are looking at Aj's that j is the first time that this lower bound is achieved, what you have is that by construction these Aj's are pairwise disjoint, and moreover the original event that we are interested in actually becomes the union of these pairwise disjoint events, because as long as the maximum of n quantities is exceeding epsilon, then there must be some j for which this lower bound epsilon is achieved. That is what you will get, that there is some aj to which your sample point must be belonging to, and therefore, you end up having this equality here, and of course, aj's are always contained in A. So, that is essentially how you end up showing that these two sets are equal. But now, let us go back to our inequality of interest. So, the Kolmogorov's inequality is about the maximum of these quantities exceeding epsilon. So, that event we have denoted by A. So, we are now looking at probability of A, but the upper bound now should be in terms of variance of Sn. And remember, the way we had proved the Chebyshev's inequality is essentially starting with the right hand side upper bound. So, again we do the same, we first start with variance of Sn and bring in the event capital A. So, to start off with, we write down the definition of variance of Sn, that it is the infimum over all second moments, and which is essentially achieved at the this specific quantity. Now, as long as you look at this expected value of Sn, we have already assumed that this quantity is 0. So, therefore, all we are looking at is the second moment of Sn's. Now, let us write down the definition of the second moment of Sn, that is this Sn squared integrated against the underlying probability measure. Now, let us bring in the event capital A like this, that we are looking at the whole integration over omega, but in particular if we focus on the event capital A, then indicator of omega is greater or equals to indicator of A. So, that is the inequality we are appealing to. Here Sn squared is a non-negative quantity, and therefore, Sn squared is greater or equals to Sn squared times indicator A, and therefore, the corresponding integrals also satisfy the similar monotonicity relation, and that gives you this inequality. So, let us continue from there. So, if you end up with this inequality, now we go back to the observation that A is the pairwise disjoint union of these events j up to 1 to n, and therefore, the indicator of the original event A is the summation of these many indicator sets. So, let us write that down, and therefore, you will end up with this summation of integrations here. So, here the integrations are now essentially focused on the events A j. Now, what we do, focusing on the events A j, it is that A j is the first event when you are looking at that fact that j is the first index when for that specific omega the modulus of S j's are crossing that level epsilon. So, therefore, what we do is that looking at that event A j, we are looking at this decomposition, focus on first S j, that is the sum of first j many random variables, and the remaining terms are these. Now, if you expand this by the binomial theorem, what you will end up with is that first you will have S j squared times indicator A j coming from the previous term, then the cross terms which is 2 times S j times this quantity again indicator of A j, and finally, you will have the sum of x j plus 1 up to x n whole squared, that integration against indicator of A j. But this final term, that is involving the sum of x j plus 1 up to x n squared of that is a non-negative quantity. So, therefore, we simply ignore that and write this inequality. So, that is still a lower bound that we have obtained. But now, let us focus on this intermediate cross term here. Now, here what is happening is that we have actually 3 terms in our integrand S j, then this summation of the x random variables from j plus 1th index to nth index, and finally, this indicator of a j. So, let us club S j and indicator of a j together and look at it. So, S j times indicator of a j actually depends on first j many random variables only and not on the remaining j plus 1 up to x n. So, that is the idea that S j times indicator a j can be purely written as a function of first j many random variables. Again, if you look at the remaining term, which is the sum of the terms x j plus 1 up to x n, that can be thought of as a function of the remaining random variables. But since x 1 up to x j, this collection and the other collection of x j plus 1 up to x n are independent of each other by our assumption, then what you end up having is that the 2 random variables must be independent, meaning these 2 are independent, since they are functions of separated classes of independent random variables, and this follows from our earlier discussion in week 2. Please refer to note 20 of week 2. But now, by our earlier observation that we have pointed out in note 6, what we can now perform is that integration of this cross term that we are interested in can now be simplified like this, that we first observe that this is the expectation of the product of 2 independent random variables. Now, as long as that happens, we also have the L2 integrability, which ensures the integrability of these quantities, the product of the random variables, and hence we can now look at as a product of expectations. So, that is the result we have discussed in note 6 earlier. But now, what we observe is that the second term here, each of the expectations are 0, and therefore, the complete term must also be 0. So, therefore, going back to the earlier relation, what we had was 2 integrations. The second integration here in the star relation, that does not contribute. So, there is the cross terms here, since they are coming from independent random variables, and therefore, the expectation of that essentially factors out, that tells you that term actually is 0, and therefore, it does not contribute. So, therefore, going back to this star relation, we end up with this lower bound for variance of S n. But let us now look at specifically each of these terms here. Now, here on A j, what we have is that modulus of S j exceeds epsilon, and therefore, what we end up with is that variance of S n can be shown to be greater or equals to this quantity, where S j squared are greater or equals to epsilon squared, and therefore, you end up having this lower bound. Now, this probability of edges, they will sum up and give you probability of A, because they are pairwise disjoint and the union of edges are actually A. Therefore, we end up with the inequality that variance of S n is greater or equals to epsilon squared times probability of A, and therefore, probability of A is less or equals to variance of S n divided by epsilon squared, which we wanted to prove. Remember, prob A is the event of question that the maximum of S j's minus expected S j's modulus values of them exceeds epsilon. So, that is the event in question, and that we have ensured that this is upper bounded by variance of S n divided by epsilon squared. Now, there is a related inequality that also tries to estimate the maximum of all these partial sums. Now, here this is called the Archimedes inequality. Here we do not assume that the random variables are coming from L2. These are any sequence of independent random variables. Now, here what we end up having is that for all epsilon positive, the maximum of modulus of S j's exceeding 3 times epsilon is less or equals to 3 times the maximum of the probabilities of individual modulus S j's exceeding epsilon. So, here we have brought out the maximum outside the probability description, and here we have to take 3 outside also, which is coming from here, and here the essentially bound that we are looking at are j by j. So, as long as we are looking at the probability of modulus S j is exceeding epsilon, that essentially gives you a relevant bound for this quantity on the left hand side. Now, here we note that first of all here we do not assume any kind of integrability assumptions on the random variables x n, just that these are independent. So, that is the first comment, and next is that in the event that we are interested in on the left hand side, we are not looking at S j minus expected S j, but rather S j's themselves, and we are asking when does maximum of S j's are getting big in the scale of epsilon, so that they exceed 3 times epsilon, and that can be controlled in terms of 3 times the maximum of these probabilities. So, that is the statement of the Ethemades inequality. So, let us try to see the proof of this. So, we consider the similar looking sets that we had considered in the proof of Kolmogorov's inequality, that here we again write the event A to be the event in question. Now, here we have the lower bound given by 3 times epsilon, and again we can ask when is the first j for which this happens. So, again we are looking at j from 1 to n, and if for first j minus 1 this happens and it is the first j when this lower bound is achieved, then we are putting that sample point in A j. Of course, A j's are subsets of A, and moreover by construction they are pairwise disjoint. And finally, the original event A that we are interested in are actually union of all these events A j. Alright, so let us now continue the estimates involving these events A j. So, the first thing that we observe is that the event A where the maximum of modulus of S j's exceeds 3 epsilon, that quantity, if you take intersection with the event that modulus of S n is less than epsilon, then you can simplify it using the distributive law of unions over intersections, and therefore, what you end up having is that union now goes outside and A j's need to be intersected with modulus of S n less than epsilon. Now, here what happens is that if you look at the set A n, that is exactly the event that all these S k's are less than 3 times epsilon for k equals to 1 up to n minus 1, and S n is the first time that this lower bound has been achieved. So, that is the description of the event A n. But now, for sample points coming from A n, we must have modulus of S n greater or equals to 3 times epsilon, and therefore, this other inequality which is modulus of S n less than epsilon is not satisfied. So, therefore, A n intersected with modulus of S n less than epsilon, that is a empty set. So, therefore, our original union of n many sets is reducing to the union of first n minus 1 sets only. Now, using this observation, what we can do is that we can now split the probability of A that we are interested in into 2 separate events, where modulus of S n is greater than epsilon and another one where modulus of S n is less than epsilon. But now, in the first event that we are looking at, that is a subset of modulus of S n exceeding epsilon. So, therefore, the probability of that is less or equal to that. So, that is the first term that we are dominating. Now, for the second term, using our earlier observation that A intersected with modulus of S n less than epsilon, that is now summation of these n minus 1 many disjoint events. So, that is what we write down using finite additivity property of the probability measure. Now, here we continue writing the upper bound of the first term in calculations. So, that we continue with and do not change it, but on the other term observe that here in A j what happens is that in particular S j's must be exceeding 3 times epsilon. So, that is what is true, but then whenever modulus of S n is less than epsilon and modulus of S j is greater or equals to 3 times epsilon, immediately you end up having the inequality that modulus of S n minus S j must be at least 2 epsilon. Now, this is what the inequality suggests, that modulus of S j exceeding 3 epsilon and S n less than epsilon. These two together implies the fact that Sn minus Sj must be greater than 2 times epsilon. Therefore, what we end up having is that the first set is included in the second set, and therefore, you end up having still the inequality here. Alright. So, therefore, we have replaced these events from the previous step with certain larger events, and here something interesting happens. So, Sn minus Sj, they are looking at the sum of xj plus 1 up to xj xn. So, these many random variables. Now, here you note that the random variables xj plus 1 up to xn, they are not dependent on the first j many random variables, but the event aj, that is precisely described in terms of x1 up to xj only, and the remaining terms therefore, are not related to them and in fact, are independent of them. So, therefore, in these events aj and modulus of Sn minus Sj greater than 2 epsilon, these two events are actually independent of each other, because they are coming from disjoint sets of independent random variables. And therefore, what we end up having is that this probability here is factoring out into probability of the individual events. So, this is simply using the independence of the events aj with these events, and this is coming from the independence of the random variables x1 up to xj, that collection with xj plus 1 up to xn. Alright. So, now what we observe is that we continue to write the first bound intact, but this term here can be dominated from above by this quantity. To see this, in each of these terms here, they are dominated from above by this quantity, and hence we end up with this maximum bound here. But now, here we have actually used the fact that this probability of edges are actually coming from disjoint sets, and therefore, their sum is actually less or equals to 1. So, that is essentially what we are appealing to. So, this as long as you take out this maximum from our calculations, then you end up having the fact. So, here there is a typo. So, this will be the summation from j equal to 1 to n minus 1 only. So, that will be corrected in the lecture notes supplied to you. Alright. So, therefore, we end up having the maximum bound coming outside of the summation, and the summation of probability of edges will be less or equals to 1. Alright. But now, note that this maximum of these probabilities, here we can also appeal to a further bound in this form, that as long as Sn minus Sj exceeds the 2 epsilon, then this is subset of the two events, that Sn exceeds epsilon as well as Sj modulus of that exceeds epsilon. So, that is a very simple inequality that we have used earlier also, and therefore, what we end up having is that probability of the event involving Sn minus Sj, that can be dominated from above by the summation of these two probabilities. So, that is what we write down here, and also we bring in this additional maximum for j equal to n, that is still an upper bound for the term that we are considering. But now, what happens is that if you take the maximum over all these quantities, what you end up having is that it is the 3 times the maximum of these quantities, that is what we have. So, as soon as you have this upper bound, we end up with this 3 times the maximum that happens here. So, this term here is not really related to j. So, that is what helps us in our estimate. Alright. And therefore, finally, this is what is happening, that our quantity of interest, which is probability of maximum of modulus of Sj's exceeding 3 times epsilon. So, that was the event in question, that now has this upper bound given by 3 times the maximum of the individual probabilities of modulus of Sj's exceeding epsilon. So, that is giving us the proof of the Ethemades inequality. But now, using this Ethemades inequality, we have very nice consequences. In particular, you note this, that in the Ethemades inequality, we did not assume any kind of integrabilities. Here, we just looked at the fact that the random variables are independent, but in the Kolmogorov inequality, we had to assume that all of these are coming from L2 as well as the fact that they are independent, and therefore, we had the Kolmogorov inequality. But now, let us try to compare the setting of Ethemades inequality together with the Kolmogorov's inequality. So, just to match the setting, what we will now do is that we will assume that the random variables are coming from the L2 space. Moreover, we will also assume that all these random variables have mean 0. Then if you use the Ethemades inequality now, here we observe that probability of maximum of Sj's exceeding epsilon, that is upper bounded by 3 times the maximum of the probabilities involving modulus of Sj's exceeding epsilon by 3. So, this is the relation that we get immediately from the Ethemades inequality, that epsilon essentially gets replaced by epsilon by 3 here, and we have a additional 3 outside the estimate. But now here we can appeal to the Chebyshev's inequality, because we have the relevant integrability, and therefore, what we have is that we can dominate it by the maximum of this variance of Sj's each term here, we end up with this specific constant outside. So, remember, as long as you appeal to the Chebyshev's inequality, each term the probability of modulus of Sj exceeding epsilon by 3 is now less or equals to variance of Sj divided by epsilon by 3 whole squared. So, that is what we are appealing to here, and after simplifying that calculation we end up with this fact. So, here also we have used the fact that here expected value of Sj are all 0. So, therefore, that is why we end up with the variance term here. So, this is why we need the mean of these random variables to be 0 to appeal to the Chebyshev's inequality. But now finally, we end up with this estimate that the variance of Sj's are actually summation of variance of variances xk's. So, this is what we have seen from note 6 earlier, that if the random variables in questions are independent, then the variance adds up. So, that is what we are appealing to here, and therefore, the variance of Sj's are maximum for j equal to n. Therefore, what we end up with is that by the Ethemades inequality and the Chebyshev's inequality, if we appeal to this argument, then the upper bound for the probability of maximum of Sj's exceeding epsilon is given by 27 over epsilon squared times variance of Sn. But remember, in the Kolmogorov's inequality we do not have that 27 constant, we just have variance of Sn by epsilon squared. So, under the same assumptions, Kolmogorov's inequality is actually giving you a sharper upper bound, where you do not have that additional 27. But in general, if you do not need to assume any kind of integrability, then you should go to the Ethemades inequality. But when you have the appropriate L2 integrability for the random variables, as well as the fact that they are independent, you should go to Kolmogorov's inequality, which is giving you a sharper bound. Alright. So, now let us try to look at another important application of theorem 6, the Ethemades inequality. So, here we first recall the fact that if you are given any sequence of random variables which is not necessarily independent, then the almost sure convergence of the series is actually equivalent to the almost sure convergence of the sequence of partial sums. Alright. But then the almost sure convergence of this sequence of random variables, which is of these partial sums, that implies the convergence happens in probability. So, therefore, if you have a general sequence capital X n, then for that if you look at the corresponding sequence of partial sums S n, then they converge in probability, that is implied from the fact that summation x n converges almost surely. So, this is a necessary condition for this series to converge. Now, this happens in the general case where we do not assume any independence on the collection x n. Now, here what we are actually going to show, that if we assume the random variables to be independent, then sequence of partial sums converge almost surely, meaning which is also same as the fact that summation x n converges, that is in the almost sure sense that happens if and only if the S n converges in probability. So, in this situation there are very specific independence assumption on the type of random variables that we are looking at, that actually implies the fact that under this hypothesis almost sure convergence is equivalent to convergence in probability. So, this is a very special case where we end up having this fact. Alright. So, let us try to see why this is true. So, in week 3 earlier proposition 2, we had discussed this exact fact that almost sure convergence implies convergence in probability. So, therefore, the forward direction of this implication that we are asking in this theorem is true. But now moreover, it is actually important that we need to show the other direction. So, now we need to show that Sn converges in probability, then together with the hypothesis that we have, we need to show almost sure convergence. So, this is the problem at hand. Now, if the convergence happens in probability, then again from our earlier discussion in week 3, what we have is that for any epsilon positive, the limit of the supremum of these probabilities is 0. So, recall this fact, this is actually coming from the fact that these are Cauchy in probability. So, this what was discussed in remark 3 of week 3. So, please go back and check. But now, once you have this Cauchy probability property, from this we will appeal to this theorem, that is the Ethemades inequality, and we will end up with a nice upper bound for certain interesting quantities. So, here what we are looking at is the maximum of these quantities, that S n plus k minus S n, modulus value of that is exceeding epsilon. So, now this happens by the Ethemades inequality, that we have this upper bound, that 3 times maximum of probabilities of these individual random variables exceeding epsilon by 3. So, this is the application of Ethemades inequality. But now note that the maximum when it is inside that event increases to this event. Here what we are observing the fact that as long as there is some omega for which this happens, that maximum of 1 up to k from 1 to j modulus of n plus j minus S n, that exceeds epsilon, then immediately you also have that it also happens that maximum of these quantities as n goes to infinity. So, that case is actually covering all such events, and therefore, you end up having this event. So, therefore, this first event increases to this, and therefore, by appealing to continuity properties, we end up having the fact that probability of this supremum is less or equal to this quantity. And therefore, by appealing to that fact from this earlier inequality, what we end up having is that this must go to 0, because the right hand side quantity goes to 0 as n goes to infinity. And therefore, by looking at this earlier relation double star, we end up having this fact, but this actually relates to almost sure convergence, and that was discussed earlier in week 3 in remark 1 part 3, that this earlier limit being 0 will be related to the almost sure convergence, and that was what was discussed in terms of again certain Cauchyness of the corresponding properties in almost sure sense. So, that was what was done in week 3's discussions. Please go back and check. But then what happens is that therefore, we have managed to show that under the assumption that Sns converge in probability, then this implies that Sns converge in the sense of almost sure convergence also. But here importantly what we are assuming is that the original sequence Xn must be independent, and therefore, we get this property for the corresponding sequence of partial sums. Alright. So, now in this lecture what we have seen is that using independence we can get some very nice estimates for the sequence of partial sums, but all of these involving probabilities of events involving the sequence of partial sums. But this is good enough for our purpose if we are interested in the convergence of the sequence of partial sums, which will also give us the almost sure convergence for the series of the corresponding random variables x n. But now what we will end up having is that these inequalities will help us get some very nice condition in terms of the moments of the original sequence x n that gives us sufficient conditions for convergences of the series summation x n. So, this is what we are going to discuss in the subsequent lectures. So, what we have essentially been covering are certain estimates involving the sequence of partial sums. which will help us get the almost sure convergence for the series summation x n. So, this is what we are going to discuss in subsequent lectures. We stop here. Thank you.